Hello, everyone. Welcome to another binary episode of the Day Zero podcast. I'm Spectre. With me is Z. Quick apology before we get into topics. This week we didn't have a new Spot the Vuln challenge, as some of you may have seen in the pre-stream. So obviously, no solution to cover there. But we should have a new one again next week. If you want to hear the solution to this one, I think this was the one, the Spot the Vuln challenge we had before we went on break. So the last binary episode will have the solution for that covered in the beginning. So, with that out of the way, we'll get into our first topic here, which is a double free in Ubuntu's account service, which was posted to GitHub Security Lab by Kevin Backhouse. This is the type of bug discovery scenario I love because this one was discovered by accident when attempting to exploit a different bug when they were preparing a demo for Black Hat last year. So Z, I'll let you get into this one.
Yeah, and I think we actually talked about the GDM3 bug that he was working on, or that he did a blog post about last year, that I believe was related to that Black Hat presentation. But yeah, with this one, I mean, he calls it a double free. You get a double free scenario. It's multiple frees there, so as a bug, straightforward. You've got this user get fallback value. The idea here is, in the particular case, it's looking up this formats locale value. And normally it might grab that out of something like your PAM environment file. Can normally grab it from there. Might look elsewhere. I'm not sure where all it looks for that, but when it fails to find it, such as with an unauthenticated user who wouldn't have like a home directory or something, it'll fail to find it, so it goes to this fallback value. This function then returns the string here, static gchar system formats local. It sees that you're looking for the formats locale, and it responds with the static pointer that they grabbed. On its own, that isn't an issue, but it is, at least to me, a little bit of a code smell. Just the idea of returning that static pointer. For any of the users, they should not free that, which is what ended up happening here. In the user change language authorized callback, it would go ahead and free this value that it got from get user fallback value. Ideally, I mean, it does have a performance hit, but you copy the value, even though it's static. That way, whatever function you're getting it from will have ownership and be required to free it, but it's just a lot easier to track ownership if you just give ownership when you return it. I think the main exception to that is during something like parsing, if you use pointers inline. Like, there are places to use it, but oh no, static values being returned, or static pointers being returned like that, stand out a little bit to me, at least. Um anyway, so that's the gist of the bug. Is just the fact that they can do this. They can basically free this as many times as they want. The post does also go into the exploitation side of it, which is nice. And I guess I'll also mention that it ended up being freed. It wasn't explicitly freed, but rather they use this macro g auto free, which I believe is just part of like the GNOME tooling or like framework and all of that. Use the macro, which ends up just marking it as auto free. So that's where the free's coming. We don't actually have the free call itself, at least visible in the source code. Um, as I said, you can basically end up in the scenario where you have this value, this string that is allocated once and then freed. Um, Sometimes once it's freed, you get a use somewhere else, you would be able to treat that as like a use after free. Because this is a read-only value, that's not the case. As a read-only value, basically it wasn't doing anything of interest there, although there was the user new function which provide kind of a read primitive on wherever this got used. If the value got changed, as long as it was a string, you could actually read it.
Yeah, I
Um,
was gonna say he talks a little bit here about an info leak. So yeah, it was pretty limited because, like you were saying, it's a string. So if it wasn't like if the address you were trying to leak wasn't a valid UTF-8 string, then you could only leak part of it or couldn't leak any of it, depending on how the bytes ended up working out. Um, And that didn't end up being too useful. Like, he didn't need the info leak, but it was there. So, yeah, it's
Yeah,
worth pointing out.
yeah, he mentions it was there, and depending on how you were to go and exploit this, like one of the first things would be looking for those sorts of primitives. Like, what do you have immediately after it gets used? And that sort of read is great. Like, I like this post because he does talk a lot about his reasoning and process, which kind of makes this a longer post that feels like it doesn't go anywhere sometimes. But I mean, sometimes that is just exploit dev where you spend your time not really too sure where to go. Ultimately, the exploit path that he ended up taking with this one was converting the double free into use after, like basically just getting two other uses that are completely unrelated to the original value. So rather than just freeing it and triggering that use after free, freeing it twice gets that memory into circulation twice. And so you have two different things writing to it and changing it, and hopefully one of them does something useful. Talks a little bit about trying to find primitives or targets for that, because it is a bit of a challenge here. This is a 20 or 0x 20 byte sized chunk, which isn't huge. It also exists as a very early allocation, which ends up placing it between a couple of, or consistently placing it between a couple of long-lived memory allocations. So one technique that you might go for here is a little bit of heap grooming, and you try to get it so on either side of it, or like two larger things can be freed, so when things around it are freed, it'll get coalesced into just one memory block, and then this 20 byte chunk can just be part of some other bigger structure that's more useful. Instead, he's kind of left with his 20 byte structure, and it's going to be stuck there. So he does talk about trying to groom this a little bit about the grooming, basically, and ended up saying that nothing really worked. But what he found was pretty much every time after the exploit ran, this user saved key file would usually be the one that ended up getting the allocation, because it's called immediately after, and it'll free the previous key file information and allocate it again. Has something in there that's the 20 bytes, so or 0x 20 bytes, so it ends up getting that a lot. Rather than trying to groom, he ended up doing what he said as embracing the chaos. And by that, what he ended up doing is he could also trigger this user saved key file with a number of other areas. In particular, he was just changing the email of one account, of like your own account, would call this function, free, and reallocate that thing. So just calling it a bunch of times until eventually, hopefully, that block shakes loose and something else ends up grabbing it. Which, I don't know, I mean, that's a nice way of going about it, I guess. It feels like you're really at the mercy of the machine when it comes to, is that going to shake loose or not? But I still thought it was a fun way to go for it. Ultimately, coming down to it, so he gets that 0x 20 byte chunk loose, something else is able to allocate it. Now he's able to go kind of the normal route of what should grab this so that you can do something useful. And he didn't find anything immediately useful, but what he found was this 0x40 size chunk that was check auth data. So this was used, message on the dbus comes in. If it needs to check for authorization, it's going to make a call out to pullkit, and when it does that, it's going to create this this check auth data structure. And inside of that is going to be a callback function, just standard old function pointer. So when pullkit replies and says like, hey, they're authorized to do this activity, it goes, checks the structure, grabs that function pointer, and actually goes and executes whatever the function pointer is. It's in the 0x40 region, so I'm not sure what they were thinking of here, why they thought this would work. And they just straight up say, I don't want to spend too much time dwelling on how I attempted to work around the 0x20 versus 0x40 chunk size mismatch. Let's just say my schemes were quite elaborate and also completely wrong. And that is honestly so true doing a lot of exploit development. You have these crazy ideas. Oftentimes they don't end up working, and you end up down these rabbit holes of spending hours on something that's like maybe hopefully going to be this crazy cool technique that works, and then it just doesn't work. In this case, he ended up walking away from his computer in frustration, comes back and realized that his scheme here just has this fundamental flaw, couldn't possibly work. I'd love to know what he was thinking, even though it didn't work. Just know what's going on in his head, but that's not included here. Anyway, what ends up happening is that he comes back later, says several hours before he returned to the computer and resumed bashing his head against the wall. He discovered his exploit worked, and now it's a question of, well, how did it work? Because as far as he knew, it wouldn't. And it kind of ended up being an accidental situation. In Polkit itself, so he was looking at structures that were being used by like the account service. And in Polkit itself that was getting called. It's running in a separate thread. That's why this whole callback thing was being used, because it's an asynchronous process. Polkit itself had a very similar structure for check auth data that was in the 0x20 region. So occasionally, what would happen is it would get used there, and he would get the double free being used with that check auth data. So talking actually, I've kind of been going into all of this, but I didn't talk about what his theory on why check auth data would work. I mentioned there's a function pointer in it. So his idea here was you'd make the safe request, change email, something that will get approved, and Polkit will say, like, yes, this is okay to go through, sees that function pointer and executes that callback. So it sees that as okay. So if he's able to get that Polkit request to go out, free the original, or, well, this is already after part of the exploits run, but free that block, get it reallocated by another request, this time to change root's password, and hope that that second request also ends up using the same memory block that the first one used, then it'll change that function pointer to the function pointer to call back on a root password change. Which Polkit then, the reply comes back from Polkit saying, yes, it's authorized. They check it, thinking it's still the change password, or not change password, change email request. That comes in, and they execute the callback. It ends up being the wrong callback because the data was swapped out from underneath it. Sorry, I kind of skipped over what he was going for there, but that's the idea of it.
Yeah, basically causing a confusion with the callbacks.
Yeah.
Yeah.
But yeah, ultimately, like, the fact that he ended up stumbling upon the right structure by accident, I mean, I like it when that happens, but also very
Never happens
annoying.
to me, but I'm not that lucky.
I've had something like that happen in a CTF where I accidentally left something running in the background that I didn't think would work, where I had already like moved on from at least, and then I came back and had the flag. I don't think it's ever happened for like a real exploit.
Yeah, I mean, one of the suggestions that you always like to put out there is when people are frustrated to just walk away and come back with like fresh ideas, and in this case, didn't even need to come back with fresh ideas. Did the work for you. It almost what happened here unintentionally was basically just fuzzing, because part of the reason that this worked and why it would eventually trigger is um, you could keep triggering this exploit on and crash the account service, but like it's going to get restarted, right? There's a watchdog process. It's going to restart any services that get killed. There was rate limiting. I think you could only do it like 5 times every 10 seconds, but you could just keep attempting this exploit over and over again until you got the result you wanted. So over time, basically what was happening with like just this continuous attempt to exploit it was you were kind of like fuzzing a strategy out, which was really cool. Um, so Yeah, I really like that aspect to it as well. There was a lot of like accidents here, accidentally discovering the bug, accidentally exploiting it. Uh, I don't know like what kind of karma this person had, but they got like they had a lot of luck on their side for exploiting this issue.
Well, I
But
mean,
still, I
like
mean,
the title says, getting root through wishful thinking.
yeah. Um, that said, though, like the strategy that they had worked out was a really cool strategy, like causing confusion with the callbacks like that. Um, and because of that strategy, they didn't end up needing that info leak that we mentioned earlier, which, I mean, if they did need that, it probably wouldn't have been a big deal anyway. I mean, like I said, you can just keep trying to exploit it. So the ASLR probably isn't too much of a problem. You'll eventually get an address that is useful to you that is a UTF-8 string, but yeah, because
Maybe. I
of the
mean,
exploit strategy,
because
you wouldn't even need that anyway.
one of the things is that with ASLR, a lot of times you're going to end up with no bytes in there, and even no bytes in the address intentionally, which is going to terminate any attempt of having a string print out. You might, although if you can get partial, so you're past like have that pointer sitting on the boundary or something. Um, yeah, I mean there are ways you can get it, but I can also imagine some ways where you're not going to get a useful pointer out of it. But yeah, I mean, I completely agree. I like the attack, and it's a data-oriented attack, basically. So this wouldn't have been stopped by anything like CFI even, or most newer mitigations. Maybe tagging. Tagging maybe could have done it. Although because it's also the
Yeah, because the
same type.
callbacks would have been tagged.
Yeah, although they are the same type of structure, so it depends on how the tagging's implemented.
Yeah, that would.
But
Yeah, I'd be interested on that angle, but obviously, memory tagging is not coming to Ubuntu account service anytime soon. So that's just like purely
I
for
mean,
fun thinking.
it's landed on Linux, so
For ARM,
well,
yeah,
yeah,
in
for
kernel.
ARM, but true kernel. But yeah, I actually don't know about the tagging on userland side.
Yeah, it would depend on its implementation, I guess.
That said, I think more of my point is like, yeah, I like the attack vector here. Yes, it takes a while. He actually mentions here, it relies on the chance and fact that he can keep a crashing account service, so it's nice and loud. Gives you a root shell even if you have to wait a few hours. He mentions, but would an attacker care? I think many attackers would care just because of one, it's loud. A lot of enterprise systems are going to see like, hey, there's this process crashing and starting over and over for a few hours.
It's a little suspicious.
Yes, it might raise a few alarms. Or it might not. There's plenty of places that just don't look for that. And to the fact that it is hours, like I'm in an actual attack scenario, I can see this, or even on red team scenarios and stuff, not necessarily like nation state or something. Like I could see it, like if it's an option, it could be used. I can imagine an attacker caring for sure, though. I
Yeah,
mean, it is a long time to be sitting there. Depending on the scenario, like you can hide that for a while too. So fair call, but I do like the attack regardless.
for sure, and a great blog post too. Did a good job exploring like the methodologies and stuff, I thought, and some helpful diagrams to understand the heap layout. Because for people who aren't super familiar with like the glibc allocator and how the heap looks when you're trying to do exploitation of it, it can be hard to get a mental picture of it. So um, the the diagrams of the chunks and stuff were really helpful, I think. All right. So unfortunately, our next report doesn't have like nearly as much detail, but it's a Project Zero report in a. It's an XNU heap-use-after-free. It's a bit funny because I looked at this issue around when it was disclosed in late December, I believe, and literally the day before the report went public, I was talking in a Discord about how iOS and XNU seem to inherit a lot of bugs from the BSD networking stack, and surprise, the next day this bug comes out and it's in the BSD networking stack. The vulnerability was in the INP join group functionality, which could be called with a set sock opt, I believe. And the cause is a race condition from the anti pattern of briefly dropping a lock and then reacquiring it. You'll see that sometimes in kernel because some function needs to be called that can't sleep for whatever reason, like it's running in a critical context. So, any time that a lock is dropped temporarily to call that function and then reacquired, that opens the opportunity for a race, depending on how the code is structured. Um, in this case, it happened in the path for creating a new membership. So when the lock gets dropped, another thread can concurrently enter the same function, INP join group, reallocate the mfilters buffer, which then frees the previous mfilters pointer from underneath the first thread. So kind of a straightforward race UAF as far as that goes. Now, this is just a bug report, so we don't really have any of the exploitation details. They just kind of explain the bug and give a POC. There also isn't any public exploit implementations that I could find yet, anyway. There might be some that have been done, but they're just not public, or they will become public later on. But I did take a brief look at the source code for XNU, because we do like to try to speculate on the exploitability of some of these bugs when we can. It seems this object would be about hex 20 bytes in size. It was a little tricky because there was a lot of macros and stuff used in the structure definitions, but I think hex 20 is around the ballpark, which sounds like it might be tricky to hit in a stable way. I haven't done XNU kernel exploitation before, but I have done kernel exploitation on other operating systems, and generally the rule of thumb is the smaller the object, the more noise it's going to happen in that free list and the harder a reallocation is to hit, because it's more likely something else is going to steal it away from you, and it's not going to be able to set up the controlled data that you would need. Hex 20 is pretty small. It's not the smallest you can get, but it is, it's not ideal. But I mean, there has been exploits before that have worked with smaller objects even than that. And given the fact that this is a UAF, almost certainly I think this bug is exploitable. I think the stability though would be a bit questionable, and kind of like what we were talking about with the last topic. I mean, stability is a good factor to look at for exploits, especially in something like XNU, where that is more of a target for nation states or whatever. Um, but yeah, I don't think the stability would be great, but I'm almost certain this bug could be exploited to some end, like getting code execution or whatever. Um, One other thing I thought I'd highlight from the report is the methodology. It's a field that we always like to look at for P0 reports because it gives some insight on the VR angle. And more interesting than not, or more often than not, it'll be like manual review or fuzz. Those are like the common two. There's not that many static analysis, but this one was actually found with static analysis. Um, and it does kind of make sense because if there's one bug type that's more well suited to static analysis than anything else, it's probably races, especially this type of race. But yeah, I just can't really recall many reports in the past that have used static analysis for the methodology. So I thought that was
Yeah,
cool.
I hadn't taken note of that this time. Um, yeah, it's interesting. I wonder. I mean, this is definitely one of those cases that you could do static analysis on because it is just lock or unlock and then or unlock dominating the lock basically. Um, you could use that to find quite a few cases of that. If you take note of the structure, like it definitely seems like something you'd find with static analysis, but yeah, it's interesting to point that out because I don't recall actually even covering any other Project Zero reports where that was the methodology. We've had manual, we've had fuzzing, but I don't know. Maybe we
Yeah,
have had static analysis. I just don't recall it. I mean, no doubt they've had other reports like that.
yeah. Overall, though, like this is one of those bugs where, um, just given the methodology that it was static analysis, it's a pretty subtle bug. Um, it's maybe fairly obvious if you look at the code and you know what to look for. Like you're looking for that anti pattern of dropping a lock and reacquiring it. Um,
Which
but
does
it's
happen
also,
without issue a lot of times too.
yeah,
Because in theory, like you drop this lock, but then whatever's actually going to be using it, like you're dropping it because it needs to grab the lock itself. So it kind of requires that it's also using the lock incorrectly, or that it shouldn't have been dropped in the first place.
yeah. Um, it's kind of a tricky situation when you're reading kernel code because, like you said, it's a common anti-pattern. It's something that you uh, that is required in a lot of cases, or you're going to blow up or deadlock the system. So you kind of have to know the nuances of the code if you were just doing manual review. And I doubt you could fuzz this very easily because race conditions are just they're hard to fuzz for in general. You have to have a lot of conditions line up. You have to have the timing line up. Um, and even if a race tests this exact scenario where you're running two concurrent threads that are running INP join group, if the timing's not perfect, then it's just gonna see that it's not interesting, and then it might never revisit it again. So yes, bugs like this are pretty much they're pretty difficult to find without using something like static analysis. And there seems to be a big push, especially at like Project Zero, towards using more SAS tooling because I've seen some of their other blog posts and reports, and you're starting to see it mentioned more and more. I think it seems to be the next stage of where they want to go. P0 has always been pretty avid behind like fuzzing, but fuzzing can only get you so far. SAS tooling is the one area that hasn't really advanced as much, and there hasn't. I don't know why. I don't know why there was so much more focus on fuzzing than static analysis, especially in like academia over the last I don't know like 5-10 years.
I would
But it seems like it is starting to
speculate.
shift more towards the static analysis as opposed to dynamic.
I would kind of speculate on two reasons. Fuzzing, it's very easy in academia to just have some that gets a bunch of results with fuzzing. That just has some novel method because there's just so much you can kind of do with that. But two, static analysis has always, like, for many years, it left I guess, a bad taste in my mouth from my experience using a lot of the enterprise SAS tooling. Things like check marks or whatever, which just, I mean, if you spend a lot of time configuring them and getting rid of your false positives and teaching about your system, it can be okay, but not even great. Like, I end up finding way more like false positives and useless reports out of them. And I feel like that for quite a while really turned me away from a lot of static analysis. Now, I was still a proponent of static analysis in terms of being like a sanity check, like understanding that's not finding very good bugs. Like, you run it as part of like CI/CD type setup. It's just consistently checking, making sure your devs aren't making like stupid mistakes. Like, that's always been a thing. But using it to find more serious bugs and like as a researcher, it has left a bit of a bad taste in my mouth because of that prior experience. And I feel like that's only more recently changed with tooling like semgrep, obviously CodeQL I've talked about plenty. Now there's Weagle, or however you're supposed to say that. It's new Project Zero one they put out that really stand in the place of assisting the researcher in doing the analysis rather than trying to be a complete tool. It's you can use this to assist with whatever you're looking for. I mean, semgrep you can kind of use it in a complete way too. Like, it's not like you can't, but they offer a lot more help than trying to learn how to write like your plugins and check marks or something. So I feel like that could be why there hasn't been as much push. And also just Project Zero has been having a bit of a push. I think actually since Maddie joined the team, where looking a lot more at variant analysis and taking former bugs, finding other cases of the same thing. And this, I'm pretty sure we've had other bugs exactly like this with the locking setup. So I can feel like that could also be part of why they're now pushing static analysis, because you don't really find well, you can find variants with fuzzing by lock, whereas static analysis makes a lot more sense for doing that variant analysis. So
Yeah, it's
that could
almost
also
designed
be,
for it.
yeah.
Yeah, no, I think those are some very good points on it. Um, and yeah, I think going forward we'll see more and more static analysis being used, especially by teams like Project Zero. All right, so for our last two vulnerabilities, we have the Vision DSP or digital signal processor. I've got crypto in my head for some reason. Digital signal processor kernel driver for Samsung's Xenos S20 phones. The first one here is a buffer overflow in memory mapped I/O. The vuln here is when the DSP IOC load graph ioctl is used on the device driver to load a custom model. Um, but when they say model, what they mean is like an ELF here, from what I understand, like a firmware.
Yeah,
So
they're ELF libraries. So it's
yeah.
loading a library.
So yeah, when they go to load those libraries for the DSP device, um, the code responsible for loading the library and the ELF segments into the memory mapped I/O regions in the kernel have multiple integer overflows here that can allow overflowing of these regions in the kernel memory. So it's not just one bug; it's kind of an entire area of bugs. Like this code is so bad that you can't really narrow it down to what's good.
Yeah, like
Um,
I was trying to write the summary on this one for
yeah,
Vault's page, and it's like I think I ultimately just wrote like
it's
multiple
terrible.
overflows because they're really like you can't even really summarize. It's just like all these calculations are things that can overflow. And this just comes down to the fact like I'm sure the developers writing this felt like this is a bit of a trusted area. They're loading a firmware. It is privileged off. You do
Kind
need
of.
to be well, so it needs to be accessed through like a service. So if you compromise the service, then you can hit it. And we've kind of talked about that before. Like a lot of kernel attacks that we've seen, or on the Android devices, like you see them going just from user line process, browser, sandbox, maybe escape the sandbox, and then go for something. You see it a lot less common where they go compromise the service, which gives them access to something else. But what this is showing is like after you've compromised that service, it's a lot of really bad code after it because it's kind of like this hard exterior, but really soft, undefended inside. That seems to be the case here. That the developers just weren't even thinking about it, didn't care about the security here. They just wrote the code thinking it's trusted, so it's fine, which is always a bad assumption.
Yeah. So the main bug that they highlight here is, well, they have a few examples, but the first example they list is like the section header size from the ELF is taken from the section header when parsing the section list, and this get section list size function will indiscriminately attempt to align the size to a 4-byte boundary, and as a result, it's possible for the size to be read as much smaller or larger than it actually is. So you can cause this discrepancy where a smaller size, because of the overflow, can be used for the allocation, but then the larger size that's not aligned would be used for the copy. That's just one example, though. There are some others that allow different primitives.
Yeah, and just
Another
that.
example.
Sorry,
Go
just
ahead.
to add on with that copy. So there's different functions here. Like there's this one that just calculates here's the entire size of everything, and then I believe when the copies actually happen, it's copying it like segment by segment, so it's not doing the same addition to actually end up overflowing it.
Yeah,
It's copying individually out, thinking that the addition's already been done. I just want to point it out. That's where the disconnect comes is because they're doing these in separate areas.
yeah. And as another example, is when they're processing segments offsets. Those too are vulnerable to integer overflow and can lead to relative out of bounds write. Unfortunately, like Z hinted at earlier, exploiting this issue would require system app or vendor init privileges. And that's because while the device driver is accessible to everybody and is even reachable by untrusted in the SE Linux policies, you need to be able to load your own crafted ELF file or library and use a custom linker rule file as well. The first condition there with loading your own crafted ELF file, they said they were able to achieve that with a previously reported path traversal issue. But the problem is, even with that, they weren't able to control the rules file. Um, and the only way you can control like the rules file and the ELF file properly is by using the parameters path in the sysfs. I think it's like sys module firmware class parameters path. But writing to that sysfs file is restricted by SE Linux. So that's where you need the system application or compromise of the system service to be able to exploit this. Um, so that's kind of where that comes into play. The second uh, vulnerability report here is very similar to the first. It's basically in the exact same like functionality, the ability to load the libraries and custom ELF files. This one, instead of being on the segment offsets and section headers, is on the uh, relocations or the rela segment. For those not too familiar with ELFs, that table, the relocation table, is very important for like linking and whatnot. And the relocation table is used for linking with like symbol table. It's used to rewrite things like jump slots for like the real virtual address of functions that are loaded at runtime that you want to call in like a library or something. Well, in the DSP driver, when it goes to look up a relocation entry and write whatever value it needs to for that rela entry, it'll pull an index from the R info structure, which is parsed from the user-controlled rela entry, and it'll use that index to do the final write for writing the jump slot or whatever. But there's no bounds checking on that index, so it's just another case of a relative out of bounds write because you can just write out of bounds of that memory mapped I/O region and corrupt kernel data. So there's a little bit of a complex code flow there. I do think these reports go a little bit too in depth on the like stack trace and how you get to the vulnerability, but the bugs themselves are pretty simple. Um, Once again, though, this bug is affected by the same restrictions as the last one. You have to be able to get your own L file and rules list loaded, so you still need a system app compromise. But yeah, like you were saying, I mean this entire area of code is just there's no way that it's been like audited in any capacity or fuzzed. Like I don't know. It's a little weird. I do kind of understand a little bit maybe like putting more priority on code that's directly accessible to untrusted or whatever, but um it's not like a system app compromise is an unrealistic scenario for an attacker, especially on something like Android. So yeah,
No,
this
it's
just seems
really
to be a
not.
really big
This,
and soft attack surface.
yeah, these bugs seem really silly to have. Um, yeah, I don't think there's much to really say about that or much to say in defense of the code beyond just I'm sure they weren't even thinking about security. That's not an excuse for not thinking about it, but yeah.
Yeah. But that's basically all the vulnerability topics that we have. We do have a few shoutouts that we want to do before we wrap up the show. Z, you have the first one here with Linux heap exploitation, which is kind of relevant to especially the first topic that we covered. So I'll let you jump
Yeah,
into that.
so I've talked about this course series before. This is from Max Camper, Heap Lab, uh, Linux Heap Exploitation. I talked about part 1 and part 2. I recommended both of them. Part 3 is now out, which is a third course about glibc heap exploitation. So this is like your house of attacks. Um, Talks about some relatively recent stuff too, like bypassing the more recent safe linking mitigation, which I think we even talked about on an episode. So like within the last couple years, um, fairly recent stuff. I haven't gone through the whole course, but given the quality of the prior ones, I'm sure this one is also fine. I just want to shout out the fact that this new one is available. At least check out, and I mean things go on sale on Udemy all the time. Looking at it right now, it's showing up for $20. I mean, I don't know if anybody buys any course for full price, but yeah, it's there. I want to at least shout it out because they have been very good courses so far.
And I wanted to shout out something that Flats released last month for the PS4. Um, so, for those who might not be totally familiar with the PS4, there has been this kind of boogeyman, I guess, that's been there for a long time for most people, which is SAMU, or the Secure Access Management Unit. It's responsible for doing cryptography, and it kind of holds the keys uh, to the kingdom to be able to do decryption of like on system stuff. Um, but there was a bug that was discovered by Flats a while ago that I thought was really cool, and I wanted to shout it out because I just love, you know, looking at crypto bugs. They're kind of fascinating to me. So one of the things that SAMU exposes over the kernel API is the ability um, to do like service encryption. So you prepare encryption requests, and you have to do HBAC in order to like sign those requests or whatever. But Flats ended up finding an issue where you could kind of brute force the key one byte at a time. So, like, this is an AES 128-bit key, if I remember correctly. So that's not something you're going to be able to brute force in like the lifetime of the universe with like a modern PC. But if you're able to brute force the key one by being able to set the key size, which for whatever reason Sony allowed you to do, um, you could just keep going through each byte of the key until the request succeeded, and yeah, you would just be able to recover the 128-bit key. So, really funny and like memeable bug, I guess, from a crypto standpoint. It was kind of funny too because there were some other, I forget who it was that pointed it out. It might have been Vladimir. Um, I think SGX had a very similar to this bug, very similar bug to this one actually. SGX being Intel's like secure guard extensions or whatever, their secure enclave technology. They also had key slots, and they had a very similar issue with this. And the context of the tweet was like, it seems nobody can implement key slots properly for cryptography. But yeah, there's not really a write up for this bug, so it's not one that we could really cover on the episode. And I don't I don't know all the details behind it because um, crypto is not my strong suit. But the POC is there, and if you want to play with it, you can. If you have a PS4 on a bit of an older firmware, I think you have to be like below 7 point something, 7.50 maybe. So yeah, if you're on that firmware, you can play around with it. But yeah, you can basically use this to dump key slots. So just wanted to shout it out. And Balika mentioned same bug that Nintendo Switch has. Yeah, so I think the extracting the Tigra keys was kind of similar, and I was actually thinking of shouting that one out too. Um, Unfortunately, I don't know if I have the link because I was gonna do this shout out as well, but I forgot. But yeah, I can put that in the description of the video anyway. But yeah, Nvidia had some similar like problems with the Switch, and there was a really good write up post about that as well. I think that was in November. But yeah, just wanted to give it a quick shout out. Flats is really damn smart and finds some really cool issues and does some cool exploits. All right. With that said, though, that's basically all the shoutouts and topics that we have for this episode. Thank you to everyone who tuned in. The VOD will be up on Twitch immediately or on YouTube tomorrow. We also have previous podcasts up on Spotify, Apple Podcasts, more links on Anchor. If you want to join the community, follow our Twitter and join our Discord. Links for those will be in chat or down below in the description. And yeah, we'll see you next week when we return at Monday for the bounty episode.